This session dedicated to understanding of second moment of area. So basically second moment of area is a mathematical term we have defined to understand the distribution of a surface or a surface point with respect to an arbitrary axis. What does it mean? If we recall the term moment of inertia, we have already studied this term in our school. That moment of inertia basically tells us the inertia against the rotational motion. That means that if I am having a body which is able to rotate about an axis, suppose the axis is xx and this body is capable to rotate about this axis, so what would be the value of torque to achieve a particular angular acceleration alpha can be defined with the help of its moment of inertia. So the torque is equal to I alpha, and this moment of inertia basically equivalent to the inertia which we discuss about the linear motion, where we talk about the force is equal to mass into area, where m represent the inertia when we talk about the linear motion. Similarly, the moment of inertia represent the inertia against the rotational motion. This is the another form of this moment of inertia, but particularly we are not talking about here the distribution of mass about a rotation, about an axis of rotation. Instead of that, what we talk about the distribution of area itself. For example, if I am having this kind of a body and I am interested to understand what is the distribution of its area about this axis. This is my axis. So this sort of thing we discussed and understand in the second moment of area. I will also explain the physical significance of second moment of area, or where it is applied particularly in the engineering field. So let's start that the second moment of area, also known as the area moment of inertia or the second area moment. These are the different names. We can call anything that the second moment of area, or sometime it is called that the moment of inertia of an area. All the terms are similar and meaning is same in all the cases. So now let's try to understand that. I have already said you that this is the moment of inertia. For example, suppose I am having a ring which can be rotated about this axis, which is passing from the center of the ring and which is perpendicular to the surface of the ring. So this sort of area which is perpendicular to surface are known as the polar axis. If I am talking about the axis which are passing from the center but in the plane, this sort of axis are known as the plane in the axis in the plane, but an axis which is perpendicular to the surface are basically known as the polar axis, and we should remember this term because it will be used for in the study of second moment of area. So moment of inertia basically represent the distribution of mass. Similarly, and what is the application? That it gives the sense that the essence of what is the value of torque required to get a specific angular acceleration. In case of second moment of area, it gives the distribution of surface with respect to a particular axis, and its application, one of the apt application of second moment of area is to find the strength of beams. Now you should understand what is a beam. So beams are basically structural members which are used in many engineering constructions, or to make the frames or to make the machines or the trusses. Anywhere where we have the structures, we need such long beams, and those are subjected to transverse loads and subjected to bending loads, where we need so wherever we are having a structure which is subjected to transverse load, required the beams. So beam may be of the different cross section. Here I am representing a square section or a cylindrical section or a C section, I section, L section. You may also see different sections like T sections or other sections. So what is the significance of different cross section? Why we only use a square section or a cylindrical section? Why? Because its manufacturing is simple. How we can make these types of structure? Basically we use the rolling process and create and rolling or the extrusion process to make the beams. But what is the requirement of the C section, I section? So let's take an example and try to understand first the beam strength, so that we will be more clear about the physical significance of second moment of area. Suppose I am using a beam and I want to use this beam to support a heavy load between these two surfaces. So here the cross section of the beam, what would be the cross section of the beam? If I will cut my beam from this point and I can see the cross section may be of the square, cylinder, IT, whatever. So this cross section have an important role in the bending strength of this beam. And in what way? This is the topic basically we study in the strength of material course. So I am not going to give in more detail here, but I will give you an essence so that you have a feel about the topic, that what you are going to study. So suppose this beam is loading this weight, and due to the load the beam is having a bending, and the bending at the center of the beam is defined by a term delta or del. So what would be the value of del? Basically governed with respect to the different sections. The strength or the deflection value of the beam basically can be defined as the strength of the beam. If the bending of the beam is large, we will say that the beam have lower strength, bending strength. Or if the beam is very rigid or doesn't show any deflection, that means the beam is very strong. And that strength is basically proportional to the second moment of area. And how we get this formula, I am not going to give this detail. If you are interested, you have to study the books available for the strength of material course. Here I am just giving you an essence that suppose I am having a T section beam, and here is the centroid of the beam, and an axis is passing from the centroid. This is the depth or the length of the beam. And I want to find that if I am going to use this T section beam at this place, what would be the deflection? So that deflection can be calculated if I know the value of I, and the deflection basically calculated by a formula. I am just giving you a formula, but I am not going in the detail, that the del can be calculated by W L cube by 48 EI, where W is the loading, L is the length of the beam. If I will talk about in this context, so suppose this is the length of the beam, so the deflection of the beam will be W L cube by 48 EI. And why 48? Because this is the case of a simply supported beam. For the different boundary condition the formula changes, but this I here basically gives you the value of del. So this basically strength is also inversely proportional to del. That is mean the strength is proportional. The 1 by del gives the strength, and so that the strength will proportional to the I. Why? Because the del is inversely proportional to I. So now I am not going to any further detail of the strength of beam, and I am just jumping to the expression of the second moment of area, and this is the mathematical expression of the second moment of area. For example, we are having an arbitrary shape body. I am particularly talking about the planar bodies because the whole syllabus for the mechanics at the undergraduate level talks about the planar sections. So here also I am taking a planar body, and suppose I want to find the distribution or the area, second moment of area of this body about this x-x axis or y-y axis. So here will be the formula. How I will calculate? First I will assume a small section area del A, and if I know the distance of the area del A about with respect to the x axis, here will be the formula to get the moment of area about the x-x. Similarly, the moment of area, second moment of area about the y-y. But let me tell you, in this whole subject we are not going to derive the formula for the second moment of area of the different body. Instead of that, what we are going to use, we are going to calculate the second moment of area for very different irregular shapes using the standard shapes, as we have done to calculate the centroid. So here I am showing you that one of the standard shape is a rectangular body. And for a rectangular body, if the centroid of the rectangular body is here, which will be at a distance d by 2 from the base and b by 2 from this side. So if I am interested to find the second moment of area about an axis xs which is passing through the centroid, generally what we call, if an axis passing from the centroid is known as the centroidal axis. So here Ixx is defined as one of the centroidal axis, and if I am interested to find AA, what I can do, I can consider a small strip with at a distance y from this axis, and if I will do the integration, finally I will land it to this formula which is defined by the BD cube by 12. And I request all of you that please remember this formula, because it is not easy to derive this formula every time, and we are going to use such formula frequently to calculate the moment of area of different sections. So for a rectangular body, the second moment of area is defined by the BD cube by 12. Similarly, if I am explaining one by one all the moment of area. Suppose this is the rectangular body, and I am interested to find the moment of area about xx axis, which I already calculated here. So it will be BD cube by 12. Suppose I am interested to find the moment of area about the vertical centroidal axis, which is passing from the centroid but in the vertical orientation. So it will be just opposite. The d and b will be replaced, and now it will be db cube by 12. So I request, or I suggest a student to remember this formula. Please remember the axis. If the axis is cutting this line, then it will be in terms of cube. If the axis is cutting this line, that means the size of this line is defined by the b. So b will be in the cubic term, and the other term which is parallel to the axis will be with the power 1. So here also you can see that this is my axis and this is the side. So b is not in the cubic term, however the d is in the cubic term. Similarly, if you want to find the moment of area of a triangular section about its centroidal axis. So in a triangle, the centroid is at a distance h by 3. If the h is the height of this triangle, this would be h by 3 from the base, and its second moment of area is defined by the bh cube by 36. Similarly, if I am interested to find the second moment of area about the y axis, it is defined by the bh cube by 48. Here very interesting term, that these two are not just interchanging its terms, but as the distribution of mass about these two sides are not representing by b and h. Similarly, these two formula are not same, and you should remember and that this is having a b cube by 48, and this is having the bh cube by 36. In my one of the session, I will definitely explain these two, how we calculate these two, but not this time. Now let's move further and understand one of the important concept, that is the parallel axis theorem. We are going to use it frequently to find the different moment of area, and here I am going to explain you that how we can find just define this term. So suppose I am having a triangle, and I know its moment of area about its centroidal axis, which is parallel to the base. So this is defined by Ixx, and I know the formula will be bh cube by 36. But I want to find the second moment of area about a different axis which is not passing from the centroid but also parallel to this axis. So here I am showing one axis AA which is passing from the base, and I am interested to find the moment of area about this axis. So I have to use the parallel axis theorem, and the parallel axis theorem states that if you want to find the moment of area about an axis, you have to use the centroidal axis as well as the area of the triangle and the distance for which you want to transfer the axis. So here I am showing that the Ixx plus area into h bar square, where h bar is what? H bar is basically a distance for what you want to shift or want to transfer your axis, or you want to calculate the moment of area for this AA. So xx and AA are parallel, and h bar is the distance between these two axes. So in my case, suppose I am having a triangle ABC, and I know that the Ixx value and I want to shift, or I want to find the moment of area about an axis which is h1 away from this and parallel to this, the formula will be IAA will be Ixx plus area of the triangle, which will be 1 by 2 into b into h, and the h1 square. Suppose I want to find the moment of area about another axis which is on the other side and a distance h2 away from this axis xx. So the formula will say that IBB, this axis is my BB axis, will be Ixx plus area of the triangle into h2 square. Now one special case where I want to convey you that, suppose I am having a case where I have a triangle and I know that here is the centroid and I am having an axis AA. For what the moment of area is given to us, means for this case a body A, B, C is having a second moment of area IAA about this line, and I want to find the moment of area about another axis which is BB and h2 distance away from AA, and AA is h1 distance away from the centroid. So now my question is that, is it possible to transfer AA directly to BB to get IBB? What does it mean? I want to say that, is it okay to write that IBB will be just IAA plus area of the triangle into the square of this distance? So let me explain it again, that if I know the moment of area about an axis AA which is not the centroidal axis, and I want to find the moment of area on another axis which is also not a centroidal axis, so is it okay for me to just transfer this axis from here to here, or no, it is not correct? So let me tell you, this is not correct, and why it is not correct, let me explain you. For example, suppose I am having a triangle and I know its centroidal axis moment of inertia is defined by just I, and the area of the triangle is suppose 6. There are two axes AA and BB. Suppose B is 4 unit distance away and A is 5 distance away, and I want to find the IBB and IAA. So as I know that from the parallel axis theorem, if I know Ixx, I can transfer Xx to either AA or BB to get the value. For example, here I am showing IBB, which will be Ixx plus area of the triangle, and the square of the distance for I am transferring here, it is h bar square. So I know that this is the 4. So my moment of area will be I plus 96. On the other hand, if I want to find the moment of area about the AA axis, my IAA will be what? Ixx plus 6 into 5 square, that is coming out 25 into 6, that will be 150. So I plus 150. So moment of area about IAA and IBB are defined by I plus 96 and I plus 150. Now let's see that if I want to find the IBB using IAA, I don't want to use the Ixx, or I want to use IAA to calculate IBB. So what I will do, I will calculate IBB by using this formula, that is IAA plus area of the triangle and the square of the distance for what I want to shift. So in this case, I want to shift it from here to here, that means the 5 plus 4, that means 9. So my answer for IBB will now become I plus 150 itself is IAA, plus these two values getting a value 486. So my new value is coming out I plus 626. So what is the correct value? Is it this is the correct or that one is the correct? So please remember, this is not a correct approach. Whenever you want to shift an axis, you have to use the centroidal axis. You cannot use any other axis, otherwise your answer will not be correct. And why it is happening? Because once you are transferring from this value from here to here, and then again you are transferring here to here, so basically you are using these distance 2 times. Once you are coming from here to here, you are considering this distance. When you are going from here to here, so you can make that you are going from here to here and then here to here. So ultimately you are mapping this distance 2 times, which is not correct. So this is one of the thumb rule, that whenever you want to shift axis, you will always shift the centroidal axis. Now quickly I am showing the moment of area of different shapes, which we are going to discuss in detail in my next lecture. But here this is the case when I am having a right angle triangle having the 2 centroidal axes, and the moment of area about the 2 centroidal axes are basically BH cube by 36 and HB cube by 36. Here you see that these 2 terms are basically going to interchange, but if you will recall that in case of a other kind of triangle which is not a right angle triangle, and if I am interested to find the moment of area about these two centroidal axes, one of the centroidal axis is BH cubed by 36, but other centroidal axis is basically AHB cubed by 48. But here if you are talking about the right angle triangle, these two values are just similar, only B and H are interchanging. In case of a circular body, the moment of area about any of the axes passing from the center are the centroidal axis, and that is defined by pi by 64 d to the power 4, where d is the diameter. In case of a semicircle, the semicircle has these two centroidal axes. So here also one of the centroidal axis which is parallel to the diameter is 4r by 3 pi distance away, and for this axis, this is my x-axis, the centroidal, the moment of area is defined by 0.11 r to the power 4. I request students, please remember this formula, because you are not going to derive this formula. You are going to use these formulas to calculate the moment of area for different sections. Similarly, for the vertical axis, it is just half of this value, so this will be half pi by 64 d to the power 4. And for a quarter circle, here is the centroidal axis, and for both the centroidal axis the moment of area are equal, and which is equal to half of this value, which is 0.11 r to the power 4 by 2. In my next lecture we are going to further discuss that the moment of area of the circular section, and then we will solve some important problem. Thank you.